Hello everyone, welcome back to the 9th lecture of Spatial Statistics and Spatial Econometrics. So in this lecture, we are going to do a quick recap of a very important topic that we started last time, which was the implications or the consequences of spatial autocorrelation for statistical estimation of mean and its confidence bands, right? So very quickly, since it's a very important topic, what we started with was an IID sequence of values Z1 till Zn. So we have a sequence of data points from Z1 till Zn, and they are independently and identically distributed sequence of random variables from a Gaussian distribution having unknown population mean mu and a variance sigma squared. Okay, and we said that the minimum variance unbiased estimator of mu was nothing but z bar. So we said that z bar is our best guess of what the population mean would be. And then we also said that look, once you construct this z bar, it is a function of these random entities zi's, and hence z bar is itself a random variable. So if z bar is a random variable, then it must have a possibility of error. That is to say that as a statistician, I cannot really say that I've known z bar with 100% certainty. There's going to be some error, some uncertainty around what this z bar value can take. And on your screens, you can see that if z bar is distributed normally, because it's a function of normally distributed random variable zi's, so z bar is also normally distributed. Its population mean is mu, right? That's the expectation of z bar, which is what we are using to to get a sense or a best guess of mu itself, and its variance is sigma squared by n. So in previous lecture we established that if you have IID random variables which are themselves normally distributed with variance sigma squared, then the sample mean has variance sigma squared by n. So it has a smaller variance than each individual random variable by itself. Then we can write out the 95% confidence interval for z bar. That is we are 95% sure that z bar will lie between this interval, that is z bar minus 1.96 sigma by root n and z bar plus 1.96 times sigma by root n, right? So what we are saying is that we have a sequence of values z1 to zn, distributed across a real number line. Here is a real number line, right? And given these values, we have some distribution, normal distribution, that is a bell curve, which each zi follows. So we have zi's, we have z1, say z2, z3, z4, z5, and so on and so forth. Okay. So z bar is nothing but the mean of these values. So it's going to be around the central tendency of these values. Now z bar can take values which are in this range of z bar minus 1.96 sigma by root n and plus on the right hand side of z bar 1.96 sigma by root n, right? So what we say is that z bar will lie in this middle area with probability 95%, okay, or 0.95. This is the case for the IID distributed sequence of data. So this is for IID, very, very important. And then we sort of relax this assumption of IID and we say all these zi's are not independent of each other. They are somehow spatially dependent. That is to say that if I am able to observe, if I realize z1, that is z value of z at location 1, then I can know something about z2, right? Because z1 and z2 are dependent on each other, and more specifically, they are spatially dependent on each other, right? So they are co-varying together. So covariance is an indicator or a measure of linear relationship. So we have this structure of spatial dependence, covariance Zi, Zj is equal to sigma naught squared times rho to the power of modulus I minus j. So this modulus, absolute value of modulus of or the modulus of I minus j is nothing but a metric of distance, a measure of distance between these locations I and j. Remember, the covariance, the measure to which or the degree to which Zi and Zj move together, which is what covariance is telling me, is a function or is a virtue of their respective locations and not the values by themselves, right? So the covariance structure only depends on the locations between and the difference of these locations I and j, right? So this is a very specific, rather a restrictive form of spatial dependent structure, but a very good point to start with. Okay, and also we are saying that, look, these are positively correlated, that is rho is between 0 and 1. If rho were a negative number, then these numbers, these entities would be spatially negatively correlated. Okay, so if I see a very high realization at a particular location on the real number line, it's quite likely that the neighboring values are also likely to be higher values rather than values on the lower side, right? So what we are saying is, if we want to sort of visualize the problem, we again have our real number line and we have our Zi's distributed across this real number line. We can just say Z at location 1, Z at location 2, Z at location 3, at location 4, keep going till Z at location n. Okay. So once I have these values, the spatial dependent structure is telling me that once I get to know Z3, there is some dependence of Z3 with Z4. So whatever value I realize at location 3 will have a dependent spillover on Z4 and also a dependent spillover on Z2. Okay, because 2 and 3 and 3 or 4 and 3 and 4 are equidistant, that is the unit of distance between these two is 1. The spillover, the degree of spillover is going to be exactly the same. That is what the covariance structure is telling me, right? Or the spatial dependent structure is telling me, right? The spillover of Z3 on Z5 and Z1 will be slightly smaller because now we will have rho raised to the power 2, right? So rho now has a power 2, rho is between 0 and 1, so rho squared is certainly smaller than rho. Okay, so the spillover, the degree of spillover that is attained on locations that are farther away from Z3 is going to become smaller and smaller, and rather it's going to be exponentially smaller because the distance is on the exponent of rho, right? All right, so that is that I believe is well understood. So with this correlation structure, I've just written down some of the covariances between different locations as examples. Covariance of Z1 and Z1, which is nothing but the variance of Z1, again something that we studied in the last lecture, right? And then covariance of Z1 and Z2 is rho sigma naught squared rho to the power 1, that is 1 minus 2 absolute value, right? And then you have covariance Z1 and Z3. Like I said, when 3 is 2 positions away from 1, the degree of spillover is going to be of the order of rho squared because the exponent is simply absolute value of 1 minus 3 and so on, right? So this is how my structure is given. By the way, this also means there's one more piece of information here, is that not only 3 is going to have a spillover on 1 is also going to have a spillover on 3. And just like that, 1 is also going to have a spillover on 2 is also going to have a spillover on 1, and so on and so forth, right? So in space, when we do spatial analysis, every location impacts what is happening at every other location, and on the other hand, every location is also impacted by what is occurring at all other locations in the domain of our study, right? How would these impacts be defined? What will be their measures? How strong they will all depend on the spatial dependent structure as specified mathematically. Okay, so these devices, spatial dependent structures, this is a device. Covariance offers, the covariance operator offers a device to specify the spatial dependence structure. Okay. All right. Just a little note before we sort of move on to the final conclusion of this exercise, that this spatial autocorrelation structure is quite similar to the autoregressive time series or serial correlation structure of first order, which is called as the AR1 structure, right? So which is, I mean, this is not very surprising. If I were to take these indices 1 to n instead of space, if I were to take them as time, right? So if I take time equals 1, 2, 3, 4, keep going till n, or I could use the notation t, it's just notation, right? All I'm saying is I am realizing values at each time period t, right? So then I have a timeline which goes from 1, 2, 3, 4 all the way till n, and I am able to specify random variables at each location that are which will have realization z1, z2, z3, and so on and so forth. The autoregressive structure of order 1, which is called AR1, basically specifies that every value that we observe at a given time period has a spillover from the previous period. Like so for example, habit persistence, right? So if we look at credit card spending of a average credit card user, then it's quite likely that the amount of spending that we observe today, a lot of it would be explained by what they were doing in the previous month or in that month in the previous year, right? The kind of consumption pattern that we would observe for someone in a cafeteria a lot of it will be explained by what they were consuming in the previous visit to the cafeteria. So the idea of the AR1 structure is that there is this one period lag spillover that happens every time period as time moves on, right? So we have a similar thing going on with spatial. However, in case of spatial, as we have seen, that the spillovers can also go in the other direction, which is not the case with time series, right? So what happens at time period 2 cannot impact what happens at time period 1, because time period 1 came before time period 2, right? So the spillover impacts are unidirectional. They can only happen in a direction. That is a fundamental difference between time series analysis and spatial analysis. Another fundamental difference between spatial data and time series data is that when we talk of forecasting, right? So if this were a time series forecasting exercise, then a typical query would be, what is the value of z at time period 1? So, for a central bank, for a finance machinery of any country or a state, the idea is, can you forecast what would be the GDP growth in the subsequent time period, right? So I've observed GDP of India from, right from independence to let's say till 2021 or 2022, and I want to now predict what will be the GDP growth rate for 2023. So I have a time series of data and I want to predict what will happen in the next step, right? In case of spatial analysis, right, we don't necessarily have to hop on one unit, right? Spatial forecasting is as good as to be done at a point like, let's say, 3/2. Any location on the real number line is a valid forecasting point, obviously including n+1, right? So that's the difference between spatial data and time series data. right? If time series started at Z1, Z0, we cannot go in the retrospect and say what was the GDP of India in 1945 using the time series from, let's say, 1948 or 1950, right? It is not possible to go back, but in case of space, that is a valid query, right? That's the difference between spatial analysis and time series analysis. Okay, so we showed last time that under spatial correlation, now what changes is the variance of z bar. So z bar remains a consistent estimator of mu, but the variance of z bar is no longer sigma squared by n. Rather, it is a value which is sigma squared by n times 1 plus rho over 1 minus rho. And in the previous lecture, we also said that we could set this value n 1 minus rho over 1 plus rho equals some value n prime. So we could sort of re-specify this variable into a more concise n prime or n tilde variable, and then sort of try and contrast between the variance of z bar in the IID case and in the case when we have spatially dependent data, right? So, and we said what we found was that this n prime, which is the new effective strength of data, if we were to represent variance of z bar as it appears in the IID case, then this n prime will be effectively smaller than n. And I said in the previous lecture that what this really means is that because of dependence in data, because of spatial dependence in data, the effective or net information available to conduct our analysis is smaller than the unique data points or unique points where you have realizations, because all these points are to a degree dependent on each other. So they effectively contain an information set which is smaller than the quanta that you see in terms of the number of realizations, that is n, right? This is very interesting, but also quite intuitive. Okay, so we learned that there is bias in variance of z bar if we ignore spatial independence, and indeed the data has that, exhibits that kind of a structure. Of course, if there is bias in variance of z bar, there is also bias in standard deviation of z bar, which is nothing but, sorry about that, which is nothing but the square root of variance of z bar, right? So if there is bias in variance of z bar, then there is bias in standard deviation of z bar. And can we quantify this bias? Of course we can quantify this bias. Well, this bias will be nothing but the true value of variance of z bar is 1 plus rho sigma squared times 1 plus rho over sigma n times 1 minus rho minus what you would have thought if you took the data to be IID and they were spatially dependent. So if you ignore spatial dependence, this value here is the quantum of bias that you're going to have to work with, right? And in the other case, in case of standard deviation, well, it will be the square root of sigma squared 1 plus rho over n times 1 minus rho minus square root of sigma squared by n, right? So this is the bias in standard deviation of of z bar. This then leads to the bias in the 95% confidence interval, right? And what we said last time is because n prime is smaller than n, the confidence interval, the 95% interval where in which I believe z bar or the mean will lie for this given population, this confidence interval is larger, right? So to be able to attain a confidence to the extent of 95% out of 100 times z bar will lie in this range, that range will become slightly larger, right? So there is a little bit more error in the data, and the reason is because you have effectively smaller set of information because of all these dependent values. And it will turn out that as the value of rho increases, that is spatial dependence increases, n prime, which is the effective size of data set, independent data points will become smaller and smaller, and the variance of z bar will become larger and larger, and hence the confidence interval will also become larger and larger. All right, so you guys can sort of, you guys should do some a thought exercise on this, before you move forward. A 2-minute thought exercise will help you understand this concept better. Okay. All right, so let's move forward. So let's try and do an example or an exercise to understand the concept, the dependence on rho of this bias of invariance of z bar and the confidence interval of z bar, that is the sample mean, for a given sequence of data, size of data set, and a given value of rho. So let's read the question. Consider a sequence of 10 data values. So now I have n equals 10. That is the apparent quantum of information. I have values observed or realized at 10 locations in space. Z1 till Zn indexed by their location on a real number line. Okay. All these Zi's, it's not an apostrophe, sorry about that. All these Zi's exhibit a spatial dependent structure which you have already seen before and you have an understanding of from earlier. And now we are given rho is about 0.3. Okay. Now rho could go between 0 and 1 if they are positively spatially correlated, right? So we still have positive spatial correlation and we have rho equals 0.26. And we are asked to evaluate an equivalent number of observations that would exhibit spatial independence given the 10 spatially dependent observations having rho equals 0.26. Okay, and this spatial dependent structure, which is covariance Zij is equal to sigma squared times rho to the power absolute value of I minus j, right? And I and j are simply locations of data index in this on this real number line, and I and j can only go from 1 to 10. Okay, and the second query is evaluate the spatial autocorrelation impacts on 95% confidence bounds for z bar. Okay, so we have a pretty good understanding of these things now. So let's look at the first question. The first question is basically asking you what is n prime, what is the effective amount or quanta of data that would be independent, spatially independent, would bring to the table, that these 10 values would bring, all together at once. So we know that for question 1, n prime is nothing but n times 1 minus rho over 1 plus rho. Okay, so I have n is 10, 1 minus 0.26 over 1 plus 0.26, which if you solve you will find that it is equal to 6. Okay, so there is an equivalent of 6 independent observations that this data set provides as far as the information that it brings to the table in order to estimate the unknown population mean mu. Okay, of course we know that z bar will still be summation I equals 1 to 10 z I divided by 10, but the variance of z bar will be sigma squared over n prime, which is 6. So we have sigma squared over 6. Okay, and that implies the standard deviation of z bar. The standard deviation of z bar is equal to sigma over square root of 6, that is n prime, right? And this value will sort of, so this value is what is going to be used to now construct the 95% confidence bounds for z bar. So the 95% confidence bounds for Z bar are given as Z bar minus 1.96 into sigma over square root of 6, comma, Z bar plus 1.96 into sigma over square root of 6. Okay. What would be the confidence bounds for the IID case? Okay. So, for IID case, we will have Z bar minus 1.96 sigma over root 10, okay, times Z bar plus 1.96 times sigma over root 10, okay. And if you were to sort of, if you want to contrast the IID case with the spatially dependent data set that we have here, then you can rewrite the confidence bounds in a more convenient form. You can say Z bar minus 1.96 times 1.3 into sigma over root 10, okay, comma, Z bar plus 1.96 times 1.3 sigma over root 10. Okay, this is 1.3 here. I suppose you will understand. This is 1.3. Okay. All right. So what this really means is that the confidence bands are 30% longer on each side from the Z bar if you were to transition from the IID case to the spatially dependent case as given in this question. And remember, this is because of the value of rho. If the value of rho increases, if it were to increase, you would have seen an even greater, extension of the confidence bounds. So just to visualize it very quickly, what we are saying is that we are given this data on the real number line. The data are all Gaussian in nature, right? So they are all following this Gaussian distribution. In one case, they are spatially dependent, in another case, they are spatially independent, right? So I have different data points, 1, Z1, Z2, Z3, Z4, Z5, Z6, and keep going all the way till Zn. Here it's 10, so n equals 10, right? And what we are saying is that, the consistent estimator of Z bar will be exactly the same both for the IID case and also for spatially dependent case. Right? So we are saying that they will be exactly the same for both the cases, right? What will differ though is the variance of Z bar and by extension the standard deviation of Z bar and the confidence bounds of Z bar. So for the IID case, I would have to go 1.96 times the standard deviation, so Z bar minus 1.96 times sigma over root n, and on the left and equal distance on the right, that is 1.96 Z bar plus 1.96 sigma over root n. So my confidence bounds for the IID case are in black ink, which is the 95% confidence interval for Z bar, okay, the hashed area under the bell curve, okay. And if I had spatially dependent data, what happens is that my bounds sort of shift rightward on the right hand side by a factor of 1.3, so it is 30% higher, right? So what I do is that I extend the right hand side bound by 30%. So I'm going to do it approximately. I'm going to extend it by about this much. So I'm going to take it forward and I'm going to take it till here. I'm going to say this here is Z bar plus 1.96 times 1.3 sigma over root n, okay, which is 10. So n is just 10. So I hope you'll be clear on that. And I'll try to go about the same. This figure is not to scale, so pardon me for that, but I suppose it makes the point. Okay. So now the area under the bell curve that I am representing using the blue ink is the 95% confidence interval or confidence bound for, that's the, there's 95% probability that Z bar will lie between these two values in blue ink, on the blue ink markers on the real number line, and the area that you're looking at will now start to sort of provide me a 95% probability under spatially dependent, structure. Okay, so so that's about it. So now we are going to sort of move on to a two-dimensional case and study, spatial dependence and its consequences on mean estimator as a next step. Okay, all right.